Now, the next step here, how are we going to introduce this carboxy carbon with cyanide? Let's actually try to go through a reasonable mechanism for that. Let's try to draw a mechanism for how these things might react with each other.
This is all reversible? Irreversible?
Let's see. This first step is definitely reversible. But cyanide is not a good leaving group, so I don't think this step would be reversible. But in any case, that's not something that we really get into too much at this point.
Is there catalyst on our tests? They take off many points for arrows if they're incorrect.
Oh, really? What, you have to draw equilibrium arrows? For, all right, some instructors don't care about that much. Okay, that's why you keep asking that. All right, well.
Is there acid involved in it, in this step, or no?
This actually is a weak acid already,
Okay, so
right? But we'll talk about the reagents for this can be confusing. I've seen a bunch of different reagents used. But let's just go through this and then we'll go through it. All right, so let's try to be careful here. This first step is reversible. We learned about that when we talked about those category 3 attacks in amines, because this nitrogen could potentially be a leaving group. However, they're not using equilibrium arrows. But you know, then later on they did another example where they didn't use the equilibrium arrows. I don't know if they would be so picky about it for amino acid synthesis. But anyway, technically this is reversible. And I wouldn't think of this as reversible because cyanide is not a typical leaving group. Right. Now keep in mind, this is not a cyanide ion yet, because this is not an ionic bond. Yeah, so with these reagents, it might be, we can't just put a negative charge on the CN. This is not sodium cyanide. So to me, it seems like the most logical thing to do here would be to protonate first.
Why didn't we just add casein?
Well, we'll talk about that in a second. I've actually seen this done in a bunch of different ways. In a sense, we really are. What really happens here is because this is a weak acid, it will be in equilibrium with cyanide ions. So there will be an equilibrium between the HCN and cyanide ions as well. So in fact, maybe you could just say you're going to use a cyanide to attack here.
Wouldn't it just be like one step instead of two?
Well, you're going to have to do a protonation at one point anyway. But you know, maybe we should do it that way. That's not the way I've usually seen it. So we would expect the HCN to be in equilibrium with cyanide ions. So the way I've usually seen this drawn is like this. So we can do it that way. I've never been quite clear about the exact mechanism for this, but we'll just get the general idea. The mechanism.
So you're going to get a minus charge on the end, which will then, but you're in acid condition, so you should protonate first.
The problem is this is only a weak acid. Because this is a weak acid, I think that explains why we usually protonate second. Usually when we're in acidic conditions, that's because we're using sulfuric acid or hydrochloric acid, but this is a weak acid. All right, and that'll give us something like this. Because this is only a weak acid, I wouldn't protonate this anymore over here. Okay. Like I say, I'm not sure exactly what the exact mechanism is here, but I just wanted to show that this is a reasonable reaction. It's reasonable to think that the nucleophilic cyanide would attack the number 1, and then this nitrogen would protonate, and then we've gotten rid of the double bond here. This is very similar to attack on a carbonyl. Here we have a nucleophilic attack on an imine, but this is still a delta positive carbon, so we don't need to worry about whether this is the exact right mechanism. We're just showing that this is a reasonable attack here. That should help us to remember what we're doing. And now putting in our numbers, here's the number 2 side chain, here's the number 1, which we want to form the alpha carbon, here's our amino group, so what's the last thing we have to do?
H plus H2O heat.
And what does that do? We've just seen that that hydrolyzes the cyanide group. So that would take us to here, and that's the Strecker synthesis.
So it's a 3-step process.
Let's see. Step 1, form the imine. That puts in the nitrogen. Step 2, add the cyanide. And then step 3, hydrolyze the cyanide. Yeah, so it is a 3-step process. That's a good point. Okay, like I said, I've erased the mechanism for this step now because I'm not sure what the exact mechanism is anyway. But we saw that it seems reasonable that in these conditions, a cyanide will attack the number 1 and the nitrogen will no longer be part of the imine. I got messed up. I should have called this the number 3.
So even like this works for secondary, but you can also do it for primary.
That's right, because after all, the side chain, notice that here the side chain was already in the starting material. The side chain is already in the starting material, so if we wanted a more complicated side chain, we could just have made this over here more complicated. For example, suppose we were trying to make valine. Well, we could make valine like this.
Yeah, we saw an example in the book where they actually made valine through this.
So if I remember correctly, this is what the side chain for valine looks like. It looks like a V. And notice that the, by the way, notice that we've talked about how this is the alpha carbon, or you saw in the videos how this is the alpha carbon. So what's a good name for the first carbon in the side chain? We could call that the beta carbon. The first carbon in the side chain is the beta carbon. So this is an important point. The alpha carbon is considered to be part of the main chain. But the beta carbon is the first carbon in the side chain. Well, in valine, the beta carbon is secondary. Well, that's no problem. We can just start with an aldehyde where this carbon over here is secondary. And then we simply add the amine group and the cyanide we're going to hydrolyze again. So the important thing to keep in mind here, I think it would be easy to imagine that this carbon was going to become the carboxy-carbon because it starts with an oxygen on it. But this is not becoming the carboxy-carbon, it's turning into the alpha-carbon. The carboxy-carbon hasn't even shown up until we add the cyanide. That's where the carboxy-carbon comes from. And this carbon here is going to be the beta-carbon. It's going to be the first carbon in the side chain. This will form the alpha-carbon, and this will form the beta-carbon. And then we can just attach whatever we want to this carbon to make any type of side chain that we want for the most part. Okay, so let's do a Strecker synthesis for glycine. What would be our starting material? Let's write down what our starting material would be if we were trying to make glycine. Good, don't forget the hydrogens here. Glycine just has a hydrogen side chain. So in this case, we just attach a hydrogen to the number 1 carbon. Remember, this is going to form the alpha carbon. This is formaldehyde, right? Now, I just wanted to mention some of the ways that I've seen this written in the book. So this seems perfectly reasonable. I would give you full credit for this. However, in the book, they simply write it like this. That is, they add ammonium cyanide in one single step. And presumably, that's going to do both of these things together. So here we have ammonium cyanide. But ammonium really just means ammonia and acid, right? Ammonium really just means ammonia and acid, so that would account for the first step. And here we have the cyanide ion. Notice that they're doing this in acidic conditions, so really we're going to have cyanide and hydrogen cyanide in this case. So it turns out that we don't need two separate steps for this, or at least that's not how it's written sometimes in the book. They wrote these together, and that would take us straight from here to here. So you should be aware that that's the way this is written.